In section 10.6 we're discussing power series. Power series is the way that we can see that these series that we've been dealing with, which normally are just a collection, addition of constant terms, each of those constant terms could be a coefficient of a term of x. And anytime that's the case, if we involve that into our series, this can represent a function of x. Now we need to think about the ways that that function of x could actually converge and give you some meaningful information. So if in my general formula within my series I have x minus c, the most emphatic way that x could converge is if x is equal to c. And you say, well, if x is just going to be equal to whatever constant c is equal to, then no matter what term that you have of your series, each term gets multiplied by a power of 0, thus making every term 0, and clearly it would converge in that case. Wouldn't be very useful, but it would converge. The next case that would make it convergent is, what if your series is going off to ridiculously small values, like 1 over n factorial or something like that? Then you could pretty much let x be any value it wants to be, and then you could say, well, it's going to converge for any x in that scenario. Now the most common scenario is case 3. There's going to be some value of r, which we're going to say is larger than 0, where our function f of x is going to converge absolutely if the absolute value between x and c, so the difference between x and c, the absolute value of that, is less than some value r. And it's going to diverge if it's greater than some value r. So we can take some value r to the nth power and multiply it by the terms of our series. And if r is a small enough value, it's going to make our series converge, but if r gets too large, it's going to diverge. Well, let's talk about how to find that value r. The most common way is to use the ratio test. So anytime you see power series, I would say 99% of the time, you're going to be using a ratio test to solve that power series. So I say ratio test is normally the best method to find r and the corresponding interval of convergence. That interval of convergence is going to be whatever value that we find c to be. It's going to be c minus r up to c plus r. R is going to be our radius of convergence. So it's how far away we can get from r. So if my problem involves something like an x minus 5, and I find that my radius of convergence is 4, then I'll be able to go up to 5 plus 4. My ending value would be 9, and my beginning value would be 5 minus 4, would be 1. So that radius of convergence is going to add and subtract versus whatever c is inside of our problem. Now, let's see this in action. First problem here, my power series, I'm giving you the series 2 to the n power divided by n. That's being multiplied by x to the n power. So in order to try to determine this, the very first thing I'm going to do is go ahead and think about, I know the ratio test wants the limit as n approaches infinity of the a sub n plus first term over the a sub nth term. So I just try to simplify out that a sub n plus 1 over a sub n first. And you'll see here in this first fraction, I try to represent this function or this series at a sub n plus 1. It becomes 2 to the n plus 1 times x to the n plus 1 over a denominator of n plus 1. My second term here, I'm just multiplying by the reciprocal of a sub n, so my numerator becomes n, my denominator becomes 2 to the n times x to the n. Now, that's easy to simplify in this case because I can see I'm going to have one more factor of 2 in the numerator, so that goes up there. One more factor of x in the numerator, that goes up there. Now, the terms that don't cancel are the n as a factor in the numerator and the n plus 1 in the denominator. So just looking at the absolute value of a sub n plus 1 over a sub n, I know I get this. Now, we're supposed to, the ratio test tells me to take the limit as n approaches infinity of that ratio of a sub n plus 1 over a sub n. And of course, it's the absolute value of that ratio. So I say I'm going to have the limit as n approaches infinity of the absolute value of this answer. Now that becomes easy because anytime you have an n going to infinity, if the degree of the numerator and denominator is the same, you just take the fraction of the leading coefficients. Well, you could think of the coefficient in the numerator to just be the group 2x, denominator 1. So this simplifies down to just be the absolute value of 2x. Now again, I know the ratio test tells me that the series will converge anytime the absolute value of the answer I get is less than 1. So that's why I'm saying that this is just as a result of the ratio test. So I say the series converges if this absolute value of 2x is strictly less than 1. Well, that gives me 2x is less than 1 or greater than negative 1. Divide by 2, and I can say, well, this is going to converge if x is between negative 1 over 2 and 1 over 2. But hopefully you remember when we talked about the ratio test, we said the ratio test is inconclusive if L is equal to 1. Well, at each of your endpoints, at 1/2 and negative 1/2, it would make this L value equal 1. You'd say if x was 1/2, this would be 2 times 1/2, be the absolute value of 1. If x was negative 1/2, it would be the absolute value of negative 1. In either case, the L value would be 1, in which the ratio test is inconclusive. So that's why I'm saying down here, since the ratio test is inconclusive at L equals 1, you have to always test those endpoints. So yeah, I get a lot of my interval of convergence just by setting whatever answer I get for L strictly less than 1, and that's the beginning part, but then I'm always going to have to test those endpoints. So I test the endpoint negative 1/2. When I do that, I just think about what it's going to create inside my series. My series in this case, the 2 to the n over n. If x is negative 1/2, then I'm going to have that multiplied by negative 1/2 to the n power. Again, I'm just plugging it back into that function, or into that series. And then I can say when I simplify that series, anytime you have the same base to the, different bases to the same power, you can multiply those bases. So I just said 2 times negative 1/2, that's going to give me negative 1 to the n power over that denominator of n. And then I can see, well, now this is an alternating series. Your alternating series test says that if you can take the limit as n approaches infinity of the non-alternating portion of that series, and if the limit is 0, then this series converges. Well, that's precisely what we can do. The limit as n approaches infinity of the non-alternating part would just be 1 over n. That is going to 0, so we can say this series converges by the alternating series test. So now that tells me up here that yes, x can equal a negative 1/2. What about the other endpoint, 1/2? I test that. So I can say, well, if I plug a 1/2 in here, it looks pretty much the same as when I plug a negative 1/2 in. It's just that now, whenever I multiply the like powers bases, 2 times 1, it's just a 1. So unlike here, I don't have an alternating series. I just have a very basic normal P series. And you might even recognize this is the harmonic series. This is the smallest possible divergent series in existence. And you say, yes, this is a divergent P series because P is equal to 1. And your choice for the P series is anytime P is less than or equal to 1, the series diverges. So we can say, well, then we cannot include 1/2 in the interval of convergence. And you'll see up here I'll always abbreviate interval of convergence. Instead of writing it out each time, I'll just put IOC. The interval of convergence in this problem is going to go from negative 1/2 to 1/2, and it includes negative 1/2, so bracket, and then a parentheses around 1/2. You have to remember the brackets and parentheses there. For another problem here, let's take a look at this power series where you have the exponential function 4 to the n divided by the factorial 2n plus 1 times x to the 2n minus 1 power. So before I can even think about this, I need to think about this ratio a sub n plus 1 over a sub n, because I know I'll be taking the limit of this ratio as n approaches infinity. Now, the absolute value of this, and the absolute value is necessary here because x could be a negative value, so this just ensures that this ratio always stays positive. So I'll have the a sub n plus 1 becomes 4 to the n plus 1, and then please notice here, if you put an n plus 1 in for this n, you would have 2n plus 2 minus 1 simplifies to be the 2n plus 1 power for that exponent. Again, all I did is I replaced n with an n plus 1, distributed the 2 throughout that group, and I'd get 2n plus 1. Similarly, in the denominator, if you replace n with an n plus 1, you would get 2n plus 2 plus 1. That becomes 2n plus 3 factorial. Now I'm multiplying by the reciprocal of a sub n, so the 2n plus 1 factorial goes in the numerator. Your denominator is the 4 to the n and the x to the 2n minus 1 power. Now when I try to simplify this, I just start gathering like terms. The exponential base 4s, the factorials, and then the x terms. So now I can see, once I look at this, then the limit L as n approaches infinity of this ratio is going to equal the limit as n approaches infinity of, I can see I'm going to have a factor of 4 left in the numerator. I'm also going to have a factor of x squared left in the numerator because I know that x is 2 powers greater. The difference between 2n plus 1 and 2n minus 1 are 2 powers of x. That's where the x squared came from. Similarly here, whenever I look at 2n plus 1 factorial and 2n plus 3 factorial, that 2n plus 3 factorial means 2n plus 3 times every integer value less than it, so it would include a 2n plus 2, and then it would be a times 2n plus 1 factorial, which all of that, the rest of that cancels with the numerator. But I still have those two terms down in the denominator. But now if I take the limit as n approaches infinity here, I can say, well, then I have some finite expression divided by an infinite expression because only n is going to infinity. So then this is going to 0. And you say, well, okay, the ratio test tells me that the series converges anytime L is less than 1. L is always going to be less than 1 in this expression. So since I can say L is equal to 0, since that denominator is going to infinity, this series converges absolutely for all x. And just to, if you had to put an interval, you'd say, well, okay, your interval is going to go from negative infinity to infinity. Now keep in mind, even when you're putting this, you're not including infinity and negative infinity. Whenever you say all real numbers, infinity is not a real number. So you say, could I plug in an infinity for x? Well, no, because then you would have 4 times infinity squared over 4 times infinity squared, which would be 1, and your ratio test is inconclusive. Don't have to worry about this in this case because you're not saying you're including infinity. You're going all the way up to an infinite number. So that allows us to say our ratio test would always be less than 1 because n is going to infinity. X can go all the way to infinity but not include infinity and negative infinity. So gorgeous problem there. Our next one here, what if we have x to the nth power divided by n times 4 natural log of n? And I'm trying to simplify it out and determine the radius of convergence and the interval of convergence. Okay, so whenever I'm doing that in this problem, I can say a sub n plus 1 over a sub n. In this problem, that ratio is going to give me, I can say, well, my numerator, if I plug in a sub n plus 1, it's going to be x to the n plus 1 power. My denominator would be n plus 1 minus 4 times the natural log of n plus 1. Again, I'm multiplying by the reciprocal of a sub n. That means the denominator of n minus 4 natural log of n goes in the numerator, and x to the n goes in the denominator. Quickly, I can see that this is going to reduce down. X to the n plus 1 divided by x to the n will leave me x, and that x is going to be multiplying the fraction n minus 4 natural log of n divided by the denominator of n plus 1 minus 4 natural log of n plus 1. Now I automatically know in my next step when I begin the ratio test that I'm going to need to take the limit as n approaches infinity of this expression. Well, as n goes to infinity, nothing happens to x. It doesn't have an n component in it. As n goes to infinity in this fraction, you just say, well, the largest term in the numerator and denominator is an n to the first power. It's going to be infinitely times larger than any constant or any logarithmic expression. So the only thing you'll do is take the fraction of the leading coefficients, which is 1 over 1. Whenever I take the limit as n approaches infinity of this becomes x times 1, which is just the absolute value of x now. So the ratio test tells me that this series converges if the answer for L, which in this case is the absolute value of x, is strictly less than 1. So that gives me that this series converges anytime x is between -1 and 1. But again, you have to check your endpoints. So when I try to check the endpoint -1, then I'll plug -1 in for x, and you can see, well, you're just going to get -1 to the n. And then I can say, well, anytime I get an alternating series, you really should think the alternating series test. And I can say, well, all I have to do is take the limit as n approaches infinity of the non-alternating part, which would be 1 over n minus 4 natural log of n. Clearly, as n goes to infinity, that fraction goes to 0. So by the alternating series test, this series is a convergent series. So I can say that means that we can include -1 in our interval of convergence. When I think about 1, I'll plug 1 in for x, and I can say, well, all right, it doesn't matter if 1's raised to any power, 1 to the n, it's simply 1. So then I'm looking at this and I can say, well, how do I know if that converges or diverges? Really easy. I can look at the comparison test and say, well, since this series, since that denominator is always less than the denominator here, because I'm subtracting 4 natural log of n, since that denominator is always less than this denominator, I know that this fraction is always greater than or equal to the fraction 1 over n. How does that help? I know 1 over n is the divergent p series with p equals 1. I've just shown that the general term of this series is larger than that general term. So if you're larger than a divergent series, you're also a divergent series. So we can say that our series diverges, and you could put by the comparison test there. That's the logic that was used here. So this is showing that 1 should be excluded, -1 should be included. Our interval of convergence is equal to the bracket -1 up to 1 parenthesis. And now you're thinking, hey, these problems are pretty cool. Absolutely. Let's look at a couple more. So number 4 here, we're looking at the summation from n equals 0 to infinity of 27 to the nth power times x minus 1 to the 3n plus 2 power. Now this one's a little harder to think about, so let's make sure we really break this one down. I know that my ratio test is going to say, let's take the limit as n approaches infinity of the absolute value of the a sub n plus first term over the a sub nth term. I didn't simplify it out up here like I did in the other ones because I can just go ahead and do my fraction all in the numerator, all in the, instead of having to multiply by the reciprocal since there wasn't any fraction in the initial problem. So I just said, well, a sub n plus 1 is just going to be 27 to the n plus 1 times x minus 1. Now, please make sure you understand where this exponent came from. I said 3 times n plus 1, that'd be 3n plus 3, plus 2, that gives me 3n plus 5. So that 3n plus 5 came from 3 times n plus 1, and then plus 2 for the 3n plus 5. Now I divide that by a sub n, which just puts your original relation back in there. So whenever you simplify this down, you can see you're going to have one more factor of 27 in the numerator, and you're actually going to have 3 more factors of the group x minus 1 in that numerator. So this simplifies down to be the absolute value of 27 times x minus 1 cubed. Now, what the ratio test tells me is that anytime the absolute value of L is less than 1, then you know that your series is going to converge. It's when it's equal to 1 that it's inconclusive. So I can say, well, clearly this series is going to converge if what's inside this absolute value is less than 1, which means 27x minus 1 cubed is less than 1 or greater than a negative 1. And then I can say, well, all right, let's divide by 27 in all 3 parts of that inequality. I did that. Then let's take the cube root. Cube root of x minus 1 cubed is x minus 1. Cube root of 1 over 27 is 1 over 3. Cube root of negative 1 over 27, still negative 1 over 3. We add 1 to each component here. When I'm adding 1, I'm thinking plus 3 over 3. Negative 1 over 3 plus 3 over 3 is 2/3. 1 over 3 plus 3 over 3 is obviously 4/3. So I know that this series would converge anytime x is between 2 over 3 and 4 over 3. Now I need to check those endpoints though. So I already knew clearly it would converge if x is 1 because you'd always be multiplying by 0. So this is saying, well, x can go up to 4/3 and x can go down to 2/3. So my radius of convergence, it's only a 1/3 on each side of that 1. It's up to 4/3, down to 2/3. But now I'm trying to show, does it include those endpoints? I check the endpoint 2/3. So I would say, well, this, when you plug a 2/3 in for x, it's going to be 2/3 minus 1. That's going to give you a negative 1/3 to the 3n plus 2 power. Now, I wanted to get this to be to the n power so I could combine it with my other term of 27 to the n. So here's what I did. I said, I know that that negative 1/3 to the 3n can be thought of negative 1/3 to the 3n times negative 1/3 to the second. Negative 1/3 to the second is just going to give me positive 1 over 9. And then that negative 1/3 to the 3n power, I can break down as negative 1/3 cubed raised to the n, because remember, power to power, you'd multiply, that'd give you back your 3n power. This is superior notation though, because now I can see, well, that negative 1/3 cubed, I can think of that as negative 1 over 27. So then I have 27 to the n times a negative 1 over 27 to the n. Well, 27 to the n times a negative 1 over 27 to the n, that combines to give me negative 1 to the n. And then you'll notice I just brought that 1 over 9 out into the front. Now, as much as that simplified down, you almost want to think it converges, but it doesn't, and you have to think about why. A series converges if and only if you can say the limit of the general term goes to 0. And even in those cases, it's not guaranteed to converge, but we can use the test for divergence here and say, well, can I take the limit as n approaches infinity of the general term of that series and show that it's equal to 0? No, never. This series is always going to oscillate between negative 1 and 1, negative 1 and 1, negative 1 and 1. So you can't say that the limit of the nth term is equal to 0. And since you can't say that, this diverges by the test for divergence. The same thing's going to happen when you try to check the other endpoint at 4/3. You would say, well, if you plug in a 4/3 here into that first part, instead of a negative 1/3, you're just going to get 4/3 minus 1. That's going to be a 1/3 to the 3n plus 2 power. Similarly, just like I did before, I can break up that 1/3 to the 3n plus 2 as 1/9 times 1/27 to the n. That 1/27 to the n multiplies the 27 to the n, and I get a 1 to the n on the inside. And again, I factor my 1/9 to the outside just like I did up here. But then I could look at that on the inside and say, does the inside of that series go to 0 as n goes to infinity? No. 1 to the n is always going to be 1, 1, 1, 1 forever. It's certainly not going to equal 0. Therefore, again, you would say that diverges by the divergence test. And our interval of convergence cannot include either endpoint. You just say the interval of convergence is from 2/3 to 4/3, parentheses around both. Last problem I want to look at with you here. What if I have n factorial times x plus 5 to the n? Automatically here, guys, you should be highly suspect to any convergence in this one because you're multiplying each term of your function by an enormous value here. Please think about what you're doing. You're saying each coefficient of each power of your function is going to be n factorial. So your fifth term, for example, 5 factorial would already be 120. 6 factorial, 720. So it's getting huge fast. So you have to be highly suspicious of this one going into it and thinking, I bet this one is not going to converge. Well, ends out, if you think that, you're going to be correct. Let's look at why. You use your ratio test. The limit as n approaches infinity of the absolute value of the a sub n plus first term divided by the a sub nth term. this is going to equal the limit as n approaches infinity. The a sub n plus first term is going to be n plus 1 factorial times x plus 5 to the n plus 1 power. Now we divide that by a sub n, which is just the term inside your series, n factorial times x plus 5 to the n. Now when I try to simplify that though, I see n plus 1 factorial divided by n factorial. That's just going to give me n plus 1. So I get that. And then the x plus 5 to the n plus 1, there's one more factor of x plus 5 in the numerator than the denominator. So this simplifies to just be the limit as n approaches infinity of n plus 1 times x plus 5. Now think about what happens as n goes to infinity. You're going to have infinity plus 1 times whatever x plus 5 is. Well, infinity times any number is infinity, so we can say the limit of this expression is infinite. Now, what does that mean in context with your ratio test? And you should say, well, you know your ratio test tells you that your series converges only if L is less than 1. Well, infinity is certainly not less than 1. So I say, since L is infinity, the series will diverge, or the series diverges for all x. Now, with the exception of when x is equal to -5 only. And if you're wondering where I got that from, please remember back in the very beginning of the notes in this section, I said there's only 3 ways your function could converge. Most of the time, we have to find some interval of convergence like we've done in the vast majority of these problems, or at least 3 of my examples. We had to find the interval of convergence. We had some value r where we could say, well, you can go on one side of your value c down to the other side of your value c. Like in the first problem, I went from -1/2 to 1/2. That's because the c in this problem was 0. So the radius of convergence was 1/2. You went 1/2 above 0, 1/2 below 0. In problem 2, again, your c value was well, 0, but that one converged absolutely, so your interval of convergence was -infinity to infinity. In number 3, my value of c was 0, my r value was 1, so I went up 1 and down 1 in that interval of convergence. In number 4, c was equal to 1 in this case, and you can say, well, then your radius of convergence, you went 1/3 above that and 1/3 below that. Your x minus c was 1, so please notice 1/3 above c went to 4/3, 1/3 below c went to 2/3. But in all of these problems, every single solitary one of them, it will always be convergent if x is equal to c. So in this one, I knew x equals 1. It was going to converge. How far away from 1 could I go? Well, I could go 1/3 down. I could go 1/3 up. So in this problem, when I'm saying it converges only when x is equal to -5, it's going back to this first one. These will always converge if x is equal to whatever the constant is. Now, if you just see an x, it's because the constant is 0. So this one I knew would converge at x equals 0, but how far away from 0 could I go? Well, I could only go 1/2 a unit to the left and right. So in this case, it's always going to converge if x is c. So since our limiting value was infinite, you just say, well, you're not going to be able to find any value of x to which this converges, with the exception of if x is equal to c itself. So we just say for this last one, since you can't choose any specific value of x to make this limit be anything other than infinity, the only value that's going to work is if x is -5 itself. That means every single solitary one of those coefficients gets multiplied by 0 to some power. And so you say, well, then they all become 0. The summation of a set of zeros is 0. That's the only term of x it's going to converge for. Gorgeous problem. Hopefully this helps you out with this power series section. It's some interesting stuff, but it takes some getting used to. So let me know if you need any help. I'll be glad to do it.